Okay, welcome back to linear algebra. The entire fourth chapter of our book is about a number that you can associate to every square matrix called its determinant. And this number, it'll play an important role in some of the theory I want to develop in chapters 5 and 6. So I can't omit it completely, but in order to develop the machinery, it'd take quite a little bit of time to work all the way through chapter 4. So the way this author has organized the book, he's kind of given us an option to skip the first 3 sections of chapter 4 and just kind of look at this fourth section in which we're going to summarize some of the properties of this thing, many of them without proofs. So I'm going to try to prove a little bit here, but this lecture, I just want to kind of go over the results in section 4.4, which the author kind of calls a summary of facts about determinants or properties about determinants. So inside of this lecture, I do want to give you an idea of how the determinant of a square matrix is defined, talk a little bit about the jargon, the parlance that people use to discuss this definition, maybe compute an example, and then just kind of highlight these properties so that when we are working in the future, we can refer to them. Okay, so it's going to be kind of light on proofs, heavy on nomenclature. The determinant is usually discussed in lower division linear algebra classes, so I'm certainly assuming that you guys have seen this before, but I hope that some of the remarks I make about them will be worth your time. Okay, so let's start by defining this structure. So I need to make kind of an auxiliary definition here. So if you give me an n by n matrix, a square matrix A, I'm going to use our typical notation denoting its entries by A sub ij. I and j both range between the same numbers 1 and n because it's a square matrix. Then by A tilde ij, I mean the matrix whose dimension is reduced by 1 in the rows and columns. It's an n minus 1 by n minus 1 matrix. And you obtain it from the matrix A by just simply deleting the ith row and the jth column from A. Okay? So if you take a square matrix with n rows and n columns, you pick any spot in that matrix, pick an ij, you delete the jth column and the ith row, and what remains is an n minus 1 by n minus 1 matrix. I mean, there's n minus 1 by n minus 1 entries, and that matrix we're going to denote by A tilde ij. Okay? So with that, I'm going to define the determinant of a matrix. The determinant of a matrix, as I said, it's a number, but more generally, it's an element of the field. So the determinant is a function. The name of that function is det, or the notation for it, determinant. And I'm going to define it recursively. So in particular, if you take a 1 by 1 matrix, then I define its determinant to be its one and only one entry. Okay. So that's the sort of seed of our recursive definition. So if you take a matrix that has more than one row and one column, then here's how I'm going to define its determinant. I'm going to take along the first row, so I'm fixing I equal to 1, and I'm going to delete the jth column, 1j at a time, take the determinant of that A tilde matrix. So that's defined because I'm doing this recursively. I multiply that by two numbers. One is the entry in the first row and jth column, A1j, and then either a plus or minus 1 depending on j. Okay, so I multiply it by minus 1 to the 1 plus j. So with this definition, we can compute the determinant of any matrix. Let me show you what I mean by a couple of examples. If we take, say, n equal to 2, so a 2 by 2 matrix has 4 entries, and they're listed there. So using this definition, I'm just going to kind of highlight as I go. What does the definition say to do? Well, I'm going to have a sum with 2 terms in it. So starting, say, in the 1, 1 position, so when I is 1 and j is 1. So that's why I'm taking a plus. 1 plus 1 is 2, and negative 1 squared is positive. So there's my plus, that's my sign. I multiply A11 by the determinant of the matrix that results when I delete the first row in the first column. Well, that's a 1 by 1 matrix, and we said that the 1 by 1 matrix's determinant is itself, or the entry. So that's what that A22 is. Okay, I'm doing the same thing here, but now I'm adding And when I move over one, this is row 1, column 2. 1 plus 2 is 3. 3 is an odd number, so that's why I'm picking up a minus sign. I take the entry, A12, and then I remove the first row and second column this time. The resulting matrix, A12 tilde, is that number A21, so that's the determinant of the 1 by 1 case. Cleaning it up a little bit, you get that probably familiar looking formula for the determinant of a 2 by 2 matrix. Cool. Once we have 2 by 2 matrices, then we can start thinking about 3 by 3s. So how am I going to write out the determinant? I've got it written here already. Let me just narrate it. I'm going to be looking at these entries, 1 comma 1, 1 comma 2, 1 comma 3. So the signs, well, 1 plus 1 is even, so it's going to be a plus. 1 plus 2 is odd, that'll give me a minus. 1 plus 3 is even, that'll give me a plus. So that's why down here I've got plus, minus, plus in my pattern. And then I'm supposed to take the entries, A11, A12, A13, those things are there. And then I have to multiply them by the determinants of the A tildes. So if we look at the 1, 1 position, if I look at A11 and I ignore the first row and first column, then the resulting matrix, you can see it there, and I'm writing its determinant. Okay, when you move over to A12, you ignore that second column in the first row. It's no big deal that those entries aren't next to each other. Stop the video for a second and make sure you understand where this 2 by 2 matrix came from. It's the remaining entries when you delete those things. Same thing for A13, except I'm crossing out the third row in the first, or the third column in the first row. Okay. And then by our previous pattern, we already wrote up there what the, oops, sorry about that, the derivative of a 2 by 2 matrix is. So you can just continue here. I don't have to recapitulate the recursive definition. I just put in the pattern for that, each one of those 2 by 2s. And then you could multiply that out. And then that's a element of the field that depends on the entries of the matrix. Okay. We won't do it by hand, but just to give you the pattern, if you wanted to take a 4 by 4 matrix, well, its determinant would be a sum. The sum would have 4 terms, and each one of those terms would be a plus or minus times a matrix entry times a 3 by 3 determinant. Each one of those 3 determinants is a sum, 3 by 3 determinants is a sum of 3 2 by 2 determinants multiplied and so on. All right, so if you started with 5 by 5s, you break it down into a sum with 4 by 4s, each one of which is a sum with 3 by 3s, and so on and so on. So heavily labor intensive, but I hope you can stop the video now and just sort of ask yourself, yeah, do you understand what I mean by this? It's recursively defined. I'm going to scroll back up so I can look at it one more time. But when I'm looking at this formula, the key part to understanding how it's recursively defined is that the determinant on the right-hand side of the formula is for a smaller matrix. So that's what I mean by recursion. Nice. Computationally intensive stuff. Here's sort of a comment I want to make that's a little bit more general. What I was just doing was so-called expanding the determinant over any row. You can actually use any, or the first row, pardon me. You can use any row or any column. So let's give a name. If you take an ij entry in a matrix, let's call this number -1 to the I plus j times the determinant of that resulting matrix. Let's call that the ij cofactor. Okay, so our definition above of the determinant of A, we were summing over the columns the 1j cofactors. Well, A1j times the 1j cofactors, right? So that's sort of another way to just sort of describe what we were just doing. So my comment is, and I'm going to offer this with no proof, but you can do that so-called cofactor expansion along any row. You can do it along any row. So I'm gonna, or column, I'm gonna illustrate that to you, say by this matrix here. Let's do this cofactor expansion, not along the first row, but along the second column. So what do I mean by that? I mean, I take, starting with the first entry, that's A12, the first entry of the first column, and I gotta think about what its I and j are. So they're 1 and 2, 1 plus 2 is an odd number, so it's gonna have the sign minus. 2 plus 2 is an even number, so it's going to have the sign plus. So if I do this cofactor expansion along that second column, then I'm going to take minus 1 because of the 1 plus 2. Maybe I should actually write it. So it's minus 1 to the 1 plus 2. And then I take the entry there, A12, and then I've got to ignore that row in the column that correspond to that entry. The determinant of the resulting matrix is A21. So I'm going to put an A21 down here, right? And then I add negative 1 to the 2 plus 2. The entry there is A22. I like this laser pointer, ignoring that row and that column. The resulting matrix is 1 by 1, and its determinant is its entry. Okay, so if we do some signs here, negative 1 to the 3 is negative 1, so we get minus A12 times A21. 2 plus 2 is 4, that's even, so plus A22, A11, and you can compare that to the 2 by 2 matrix that we determined above, the determinant of it, where I wrote it in the order A11, A22, minus A12, A21. Those things are the same. All right, so it's not a proof, but what my comment is that you can do this cofactor expansion along any row or any column, and it won't affect the value of the determinant. It can be very handy because it's very nice to do the cofactor expansion along a row or a column. It's got a lot of zeros. Yeah. If a lot of these entries that you're multiplying by are zeros, well, then it can significantly cut down the amount of computation that you have to do. Cool. So having said that, let's start looking at some of these properties of the determinant. I think there's 8 or 9 of them or something, and I just kind of clipped them from the book. So the first three properties of determinants, I'm certainly not going to read these things out loud, but in a nutshell, what these first three do, they say what the effect of the determinant is, or what the effect of elementary row operations on the determinant is. Right? So if you perform, say, a type 1 row operation, or columns, so if you interchange 2 rows or 2 columns, the effect on the determinant is that it changes sign. Okay. If you do a type 2 elementary row operation, you multiply a row or a column by a non-zero number k, then the effect on the determinant is that so B is obtained by multiplying every entry in the matrix A by a scalar k, then the effect on the determinant is to also multiply by that scalar k. Okay, so if you multiply every entry in the row of A by 2, you doubled the determinant of the resulting matrix will have twice the determinant. If you do a type 3 elementary row operation, this is kind of surprising to me because the third elementary row operation is in some sense the most complicated one. It has no effect on the determinant whatsoever. Okay, so when you do a type 3 elementary row operation, you don't change the determinant at all. I'm not going to prove these things. The proofs of most of these properties of determinants would require us to delve much deeper into the theory of determinants. That's what's in sections 4.1 through 4.3. If somebody's interested in it, I'd love to kind of help guide your reading. If you want to look at that, you'll learn some things about multilinear functions in general. The 5th section in chapter 4 actually is a characterization of multilinear functions that act like the determinant. So there's a lot of interesting math here, but I'm just making an executive decision that I'd rather talk about inner product spaces and diagonalization. And we just have 6 weeks left in the course, so I'm not going to spend a lot of time in chapter 4. Okay, let's look at the author's example of why these things would be useful. Row reducing a matrix, performing elementary row operations simplifies the matrix, so you can keep track of how the determinant changes and record the results. So let's look at this example. So suppose you have some matrix A. It's a 4 by 4 matrix. It's written right here, and you want to compute its determinant. Well, you could just start doing cofactor expansions, right? You say, well, it's 2 times the determinant of this 3 by 3, minus 1 times the determinant of that 3 by 3, and so on. But that's kind of a lot of computation. So instead, what's the author doing here? They've done some row operation, and in particular, they're being a little bit clever here. So what the author has done is taken this 1 in the first row and second column, and using 3 elementary row operations has zeroed out the entries below that, okay? Those are type 3 elementary row operations, so the determinant isn't changed, okay? So now the author is going to do a cofactor expansion, but the cofactor expansion is going to be along that column. It's going to be along that column. 3 of the 4 entries, or summons rather, are 0. So that's why that's kind of slick. So you're expecting 4 terms here, but 3 of them are zeros because of those zeros. Okay, so what do we get here? Well, there's a 1. That's because this entry is a 1. There's a -1 to the 1 plus 2. That's because that's the 1 comma 2 entry. And then there's the determinant of the matrix that you get by ignoring that row in that column. So you can stop the video for a second and see that that's what the author wrote right there. Okay, same kind of idea. Using elementary row operations, type 3, you could take this -1 and zero out those two things, right? Type 3 doesn't change the determinant. I wrote a minus sign out here. That's just because the coefficient 1 times -1 cubed is -1. And then I'm going to do the same thing. Let me just sort of keep track of these minus signs. So the first one is the one from above. The second -1 is because I'm cofactoring with that number right there. That number's in the 1, 1 position. So I multiply by -1 to the 1 plus 1. And then I ignore that row in that column, and I take the determinant of the resulting 2 by 2, which from the pattern we established above is this product minus that one. Okay, so when you're all done, you can check that the arithmetic works out to 102. So it didn't eliminate all of the computation, but it certainly was less computation than just chugging it out, cofactor expanding along the first row of this thing according to the opening definition. That would have been 4 3 by 3 determinants, each one of which is 3 2 by 2 determinants. The arithmetic would have been much more intensive. Okay, so the point of the example is the effect of row operations. 2 more properties. These are just enumerated like they are in the book. So for properties 4 and 5 of the determinant. First of all, if you have an upper triangular matrix, its determinant turns out to be just the product of its entries. I'm not going to call what I'm going to write here a proof, but I am going to try to convince you that that's true. If you wanted me to take the determinant of A, well, I would cofactor expand along the first column. So if I do that, because the first column is position 1, 1 in the top row, 1 plus 1 is even. So I would just get 1 times A1, 1 times the determinant of the matrix that results from eliminating that row and column. Well, that matrix is also upper triangular. So if you like, by induction, the rest follows. But if we just sort of continued the pattern here, now I would cofactor expand along this column. So I would get in the 1, 1 position there, or 2, 2. 2 plus 2 is 4. So I'd get a 1 times A2, 2 times the determinant of the remaining thing. Oops, it doesn't matter. And so on. So when you're all done, cofactor expanding there, if you like, or just use induction after you do it once, the determinant of that thing would just be the product of its diagonal entries. Okay, so it's an important fact that in particular, the identity matrix is a triangular matrix. And the product of its entries would be a product of ones, and that's going to equal 1. Cool. Fifth fact, which I also want to kind of sketch a proof of, is that if you have 2 rows or columns of a matrix that are exactly the same, the determinant's 0. This is kind of a cool proof. If you have 2 rows that are exactly the same, then swap them. Let B be the matrix that you get from A by interchanging the identical rows. Well, if you interchange identical rows or columns, then you don't change the matrix, right? But swapping rows was supposed to negate the determinant. So if you have a number that, I mean, if B is equal to A, then the determinant of A is equal to the determinant of B. But on the other hand, they have to be opposites, right? So the only way that a number can be its own opposite is if that number is 0. So if you swap, if you have 2 rows or columns of a matrix that are exactly the same, then the determinant has to be 0. You can think about cofactoring too. If you have a matrix that has a row or a column that's all zeros, the determinant has to be 0. You can prove that using an idea like this, or you could prove that using elementary row operations and so on. Nice. Okay, continuing along here. I guess I said there were 8. There's 9 total things. I'm going to put an asterisk number to number 6. To prove it, we would definitely need to develop more machinery about the determinant. So I'm not going to offer a proof of this, but it is an extremely important fact that the determinant of a product is the product of the determinants. Maybe somebody would do a little class presentation if you have some time to read the material in section 4.1 to 4.3 and sort of give us the crux of the proof of that, but I'm just going to mention it here. It's very important. Seventh one is that a matrix is inverted. This you certainly in lower division linear algebra, some of you guys have already used this, that a matrix is invertible if and only if its determinant isn't 0. Okay, and then a very important formula that follows actually from 6 is that the determinant of the inverse is 1 over the determinant of A. Okay, so that's an important fact about the invertibility and the relationship to determinants. A matrix and its transpose have the same determinant. Okay, so when you, and you could pretty much sketch a proof of that from our definition. Because if you think about doing, say, like cofactor expansion along a row in A, that should be sort of the same as the cofactor expansion of the corresponding column in A transpose. So if assuming that you can do this along any row or column, it's not hard to prove 8, but I'm just kind of burying the details in another fact. And then finally, the 9th one, if you have similar matrices, you have the same determinant. Let me remind you what similar means. If A is similar to B, then one of them, B, it doesn't matter which one, is the product of some matrix P, invertible matrix P times A times P. So that's the definition of similarity. So if you took a look at the determinant of B, you could write that as the determinant of P inverse times A times P. And then using property 6, which I just scrolled off the screen, that's the determinant of P inverse times the determinant of A times the determinant of P. And then using property 7, which is still barely visible, the determinant of P inverse is 1 over the determinant of P. Okay, 1 over meaning the multiplicative inverse in the field F, if the field isn't the real numbers. But the determinant of P times its multiplicative inverse is certainly 1. So you're just left with the determinant of A. Okay, so to recap, we are not going to spend the time in chapter 4 to develop all of the machinery carefully about this determinant function. I'm going to try to use the determinant function kind of minimally, but there will be a couple of places where when we want to develop this theory of eigenvectors and eigenvalues that in particular, we're going to be using this idea that a matrix is invertible if and only if its determinant is non-zero. So I can't avoid using the determinant completely in our future work, but I don't want to burn up. It'd probably take a week of class, I'd say, to carefully move through those 3 sections of chapter 4, maybe even a little bit more. And I would rather show you something about eigenvectors and values and inner products. Okay, so thanks for your attention.